Hello, my name is Abed Kazem Targhi. I'm a PhD student at Arizona State University. I'm working at Power Electronics and Control Engineering Lab, supervised by Dr. Ayem Malik. In this video, I want to explain our research on the project titled Active Compensation-Based Harmonic Reduction, or ACHR, technique to mitigate the power quality impacts and specifically the dominant third harmonic of the EV charging systems. Here you can see the overall architecture of an EV charger, including the EMI filter, AC/DC PFC rectifier, and then the isolated DC-DC stage, and finally the EV battery. Here, because we are studying the harmonics and power quality at the input side of the EV charger that's connected to the grid, we are focused on the operation of the AC/DC PFC rectifier, and we aim to analyze and model the bridgeless totem-pole PFC in the boost operation, and to check the circuit equations and to see what's the root and reason for the third harmonic and other higher order harmonics in the input, and how we can mitigate the dominant third harmonic. Here you can see the totem-pole boost PFC, the circuit operation and the different modes. Typically there are two legs in the PFC, and one leg, including two switches, operate at the grid line frequency, that's 60 Hz, and the other leg operates at the switching frequency that we have selected 100 kHz in this project. Depending on the status of the four switches, we have four modes, depending on the input voltage, if it's on the positive half cycle or negative half cycle. And in the first mode, you can see that in the positive half cycle of the input voltage, two of the switches S2 and S4 are switched on, and it's magnetizing the input inductor. In the second mode, the input voltage is still in the positive half cycle, but so the S4 is still switched on, and here S1 is switched on instead of the S2 in comparison to the mode 1. And in the similar manner, we can now analyze the operation of the circuit for modes 3 and 4 when we are in the negative half cycle of the input voltage. If we analyze the circuit equation of the input power as the multiplication of the input voltage by the input current, we'll have two terms, a fixed term and a cosine term with the double frequency of the grid frequency. If we consider a lossless system and consider this equation at the output side, the fixed terms goes to the load, that's the battery, that's the EV battery, and the cosine term, that's a high frequency term, is absorbed by the output capacitor to minimize the output voltage ripples. And from this term, we can calculate the output capacitor current that includes the same double frequency term. And from the current equation, we can extract the output voltage ripple. That's still the sine 2 omega t term in this equation. But if we considered these equations in the closed control loop, we have outer voltage loop and inner control loop as part of the control structure of the totem-pole PFC. Here, as we had the double frequency term in the output voltage, we will have here in E1 signal, in the error 1 signal here, that goes through the PI controller of the voltage controller, and then we will have the same double frequency term at the output of the PI controller. And this one, the G signal, is multiplied by input voltage. That includes the sine omega t term to form the reference for the current control loop. So here, our current control loop, that's the multiplication of the sine omega t with sine 2 omega t and cosine 2 omega t, will have the 3 omega t term, which is actually the main reason that the third harmonic has appeared in the input current of the EV charger, because the input current tries to follow the pattern of this reference current. And finally, after the PI controller of the current loop is tuned very well, in the ideal case, we will have the third harmonic term in the input current of the EV charger. So that's the main reason that the third harmonic is created within the control loop, while the signal is pathing and following the reference values. So the main advantage of the PFC is that it converts the AC input to the DC and provides the unity power factor at the input side. But the disadvantage is that the normal operation of the PFC leads to the third order and other higher order harmonics at the input of the EV charger. So we have proposed a new method called active compensation-based harmonic reduction, or ACHR technique, to remove or mitigate this existing third harmonic within the control loop. As you can see here, at the output of the voltage control loop, we have added a low pass filter followed by a band stop filter. And the band stop filter is aimed at mitigating the third order harmonic. And it's highly dependent on the frequency that we want to stop and remove from the spectrum. And to have an accurate value to mitigate, we added a PLL unit here that checks the frequency of the input voltage, and according to the grid line frequency, according to the accurate value of the grid line frequency, it tries to remove the third order harmonic of the input. For example, if it's pure 60 Hz, it tries to, the band stop filter tries to remove the 180 Hz component from the spectrum. But if it's deviated from 60 Hz, it calculates the 3 times of the input frequency and removes that harmonic from the spectrum. The important thing is how to calculate and how to design the band stop filter. Here we can see the transfer function in a digital domain for a band stop filter, with the parameter including the center frequency that we set it for the third order harmonic. We need to assign the 3 dB bandwidth in radian per samples, and also we need to have the center frequency in hertz and sampling frequency to design the band stop filter. For example, here you can see the calculations for the design of the third harmonic mitigation of the band stop filter with the center frequency of 3 times of the line frequency, and band stop, the 3 dB band stop is calculated here according to the sampling frequency that we have selected, 10 to +5 in this project. And finally, we can extract the transfer function of the band stop filter in digital domain that we can implement in the DSP code. Here you can see the frequency response of the ACHR technique, and you can see the body plot. From the body plot, you can see that it's able to keep the first order and the I1 magnitude unchanged. It can keep the phase of the first and the fundamental harmonic unchanged. It's able to mitigate the I3 harmonic magnitude by adding the bandstop filter. And also from the phase diagram, you can see that the closed loop system is stable and it can operate very well. And now we have implemented this digital band stop filter followed after a low pass filter, and the band stop filter calculates the center frequency according to the value measured by the PLL unit. And we implemented this digital filter in the DSP code of our hardware TPFC. Here you can see the hardware image. That includes the voltage sensors, the buffers for the sense signals, the controller board that we have used the TI TMS 320F 28335 DSP model. You can see the MOSFET driver circuit, and here we have the MOSFETs. Two of them are at the upper side and two of them at the bottom. Here you can see the output capacitor and the input inductor, and with this specification of the circuit. In this slide, you can see the experimental results for a 500 watt operation of the totem-pole PFC with the input voltage of 85 volts AC RMS. Here you can see the important waveforms, including the output voltage that's fixed on the 400 volts with the minimum ripple. Here you can see the input voltage that's almost 85 volt AC RMS. And here you can see the input current with the phase lag of only 9 degrees with the input voltage, and the AC RMS of the input current is 6.2 amperes. And here we have compared the THD, total harmonic distortion, and the I3 magnitude of the input current without and with applying the ACHR technique. Before applying the ACHR technique for the base case, you can see that for the 180 Hertz, that's the third, corresponding to the third order harmonic, it has the 244 milliamperes magnitude, and the THD for this waveform is 4.88%. While with applying the ACHR technique, the I3 is reduced to 130 milliamperes, corresponding to the THD of almost 4%. That's very effective and useful in terms of reducing the THD by applying a digital filter that doesn't need any additional hardware or any change in the hardware, or that saves the power density, and we don't need to use any additional hardware to increase the volume of the circuit. And here we have compared the results from the simulation and the hardware outcomes. Here the left one is for the without ACHR technique and is compared with the right figure after applying the ACHR technique. Here you can see that the third order harmonic is reduced with applying the ACHR technique, and the third order harmonic is reduced in simulation for 47%, and in the hardware result it's reduced up to 46%. That's pretty close between the simulation and the hardware. And also the other point is that the other high order harmonic are unchanged due to the operation of the band stop filter, but it's because it's only focused on the dominant third order harmonic to mitigate this harmonic order, not the other higher ones, and with the aim of don't impact the dynamics of the system and the operating time and everything. So that's the main contribution of this work, to use a band stop filter with a low pass filter and the PLL unit that can be implemented digitally in the totem-pole PFC DSP, and it checks the control loop and minimizes the third order harmonic in the circuit, and finally reduces the THD corresponding to the improved power quality operation of the EV, especially when we have numerous EVs and the high penetration of the EVs in the power grids. It's very useful to use this technique to have a better power quality in the power distribution systems. Thank you so much for your attention. You can send me an email if you have any questions regarding this work. Thanks.